For those of us with a particular fascination for robots, we need a special understanding of the robot heart. The unromantic among you, no doubt, call the robot heart a battery. Inside a battery, chemical reactions occur which involve a transfer of electrons. Reduction, or a gain of electrons, occurs at the cathode. Oxidation, or a loss of electrons, occurs at the anode. Reduction, oxidation, redox is the name given to these battery reactions. Since an electrochemical cell of this type can be designed using a wide variety of materials, we can personally build a heart for our robot. But before we get heartistic, let's consider a few basic principles. If we take a chunk of zinc metal and drop it into a solution of copper sulfate, wait a few minutes, and the zinc becomes covered with a brown substance. Also, we note that the blue color of the solution fades. Let's imagine that we have bionic eyes so we can see what is going on inside the solution. The atoms of zinc are surrounded by water molecules, as well as copper ions and sulfate ions. The interaction occurs between the copper ion and the zinc atom. So let's focus on these two. Copper holds on to its electrons more strongly than zinc. So a copper ion attracts electrons away from a zinc atom, which becomes a colorless zinc ion and floats off into solution. As a result of the electron transfer, the copper ion has become an atom of metallic copper. As the zinc atoms change to ions, the zinc metal gradually disappears. It is replaced by the copper atoms that are created, producing a brown deposit. The removal of the blue copper ions causes the color to disappear from the solution. In the interaction between the copper and the zinc, the copper ion acts like a bully, which attacks the zinc atom, seizing 2 of its electrons. There are other ions, like mercury, for example, which can take electrons away from the copper atom. And there are atoms such as magnesium, which will give up electrons to zinc ions. It's as if there is a pecking order among ions, allowing chemists to list them in order so that those which are more easily reduced are placed on top and those which are increasingly difficult to reduce are placed on the bottom. This list is called the activity series and includes many other elements. But for now, let's concern ourselves with 2 of them, zinc and copper, and see how this difference in the tendency to become reduced can be used to construct an electrochemical cell. We've already seen how the copper ion and the zinc react. Once again, a zinc atom loses electrons to a copper ion. Now, if these 2 elements can be separated, but still made to react, then a flow of charge will take place between them. With the right equipment, we can harness a flow of charge. Time now to get artistic and build our robot an electrochemical cell using zinc and copper. First, we must keep the zinc and copper apart by creating separate half cells. In one, we put a metallic zinc electrode immersed in a solution of zinc sulfate, which will dissociate to form aqueous zinc and sulfate ions. In the other, we place an electrode of metallic copper and a solution of copper sulfate containing copper and sulfate ions. Let's connect them with a wire so that the electrons can flow from one electrode to the other electrode. But nothing happens. That's because our circuit is incomplete. We have a highway for charge to flow in one direction, but not in the other. To provide the link, we will use a salt bridge, which contains ions such as potassium and nitrate. Let's see if we can figure out why this works. We know that zinc is more easily oxidized than copper. Perhaps zinc acts as an anode, with zinc atoms giving up 2 electrons per atom. The resulting zinc ions would enter the solution, and the electrons released from the zinc could flow through the connecting wire to the copper electrode. Since copper ions are reduced more readily than zinc ions, the copper electrode could act as a cathode where copper ions are reduced, gaining electrons. This would cause them to form copper atoms, which would stick or plate out onto the electrode. If we watch a cell as it works, sure enough, the zinc electrode gets smaller as the zinc atoms become ions and drift into solution. On the other hand, the copper electrode becomes larger as copper atoms plate out on it. The flow of charge seems to be what we've predicted. So, why the salt bridge? Because without it, there can be no current flow. Why? Well, in the anode half of the cell, there would be a buildup of positive charges. And in the cathode half of the cell, positive ions are removed, so there is a buildup of negative sulfate ions. This buildup of opposite charges is called polarization, and it quickly causes the electron flow to stop. It is the salt bridge that prevents a buildup of positive charge. In the zinc half of the cell, it allows the positive ions to migrate to the opposite cell. In the copper half of the cell, negative ions can migrate to the opposite side. Together, these migrations prevent polarization from occurring. This process gives the impression that negative charges are being attracted to the negative terminal and positive charges to the positive terminal. Of course, it's the flow of electrons that makes an electrochemical cell useful. The flow of ions is also essential to an electrochemical cell to complete the circuit. But wait now. Before you install this piece of artwork in your robot, are you sure it'll do the job? After all, there are so many different redox reactions to choose from. However, you don't really need to build by trial and error. Chemists have developed ways of predicting the energy output of many different chemical combinations used in the electrochemical cells. And that's the subject of our next chapter.